So the analogy between deep learning and human brain is the popular one. So the essential it is essential to understand the limitations and the complexities of the both systems. So to begin with, let's discuss the basics of the neural network. So when we are implementing the neural networks, uh, so it's like the brain. That is really easy to say, or that is really some statement that will give you some sense of importance. But is it similar to brain? No one knows. So this is the neuron in our neural network in deep learning, basic linear regression, and this is our neuron in the actual human brain, right? This is how it looks like, right? And these are it's some uh, so it gets input from here and it transfers from these things and get out it gets output from here. That's all it is about the normal neuron. And to begin with, let's discuss the basics of neural networks. When we are implementing the neural network, we perform forward propagation and back propagation. The forward propagation is the process which involves passing the input data through the multiple layers, and while back propagation is the thing which involves adjusting the weights and biases to the of these layers to minimize the errors between the predicted and actual outputs. Now let's delve into the brain analogy. At its core, a single biological neuron receives inputs from other neurons, performs a simple trace holding computation, and then it sends electrical signal down to its axon if it fires. This is the process can be likened to logistic regression unit with the sigmoid activation function. However, this analogy is oversimplified. So with these aspects of the neural processing are similar, the human brain's complexity is far which exceeds our current understanding. We don't fully understand or comprehend how neurons learn and adapt in the brain. For instance, exactly how neurons in the human brain learn is still a mystery, and it is unclear whether humans use algorithms like backpropagation or gradient descent. The human brain may employ fundamentally difference in the learning principle that is unique to our biological system. In contrast, deep learning models are incredibly good at learning complex functions, such as input output mappings in the supervised learning. They can learn very flexible functions by adjusting the weights and biases of their layers. While the analogy between deep learning and human brain might have been useful once, it's largely become outdated. The field has moved beyond the simplistic explanation, and I no longer use to describe my work. That being said, computer vision has taken inspiration from the human brain more than any disciplines that apply to deep learning. So, discussing deep learning, it is essential to focus mathematical foundations and algorithms that rather than relying solely into the brain analogy. So to illustrate this, let's consider maths behind the forward propagation and backward propagation. Given the neural network with the n layers, each layer has L inputs and C outputs. The weights and biases of each layer are represented by matrices W and B respectively. So forward propagation is it's something like G1, which will equal to sig summation of I equals to 1 to n. Let's try if this gets we can make sense of this thing in here. Okay, we cannot, so never mind that. So I'll just write that thing for us. Z1 equals to summation of I equals to 1 to n w x I plus b1, where zi is predicted output, w11 is the bit matrix, and xi is the input. The output of each subsequent layer can be computed by applying nonlinear activation functions such as the ReLU or sigma. For example, z2 is equal to summation of I equals to 1 to n, where w21 zi plus b2, where z2 is predicted output of the second layer, where backward propagation is like to compute the gradient descent of the loss function with respect to weights and biases. We need to perform backward propagation. This involves computing error gradients using each layer using the chain rule, which looks like so. This is our basic chain rule. If you don't understand what I'm writing, just go in the previous videos. I have explained what are these things mean in the dedicated video. So where L is the loss function and zk is the predicted output of the kth layer and wij is the weight of the matrix. So using mathematical framework, we can implement forward propagation and backward propagation in the Python code, and we are going to take that code here. So this is our basic Python code where we implemented the forward and backward propagation. So I'll just take this and paste it somewhere here, which will make the whole thing more visible. So this is our Python code for forward propagation. So this is L, this is C, number of inputs, outputs, the weights and biases, W1, W2, just the things that we written previously. Then the loss function, the input data, and the backward propagation, weights and biases, all these things, and the loss gradient. So that's the basic thing. This code computes the forward propagation and backward propagation of the simple neural network with 2 layers. So the weights and biases are updated using the gradient descent, SGD, stochastic gradient descent, to minimize the loss function. Please note that it is just a basic example. In practice, you would need to handle much more complex scenarios such as regularization, Bayes normalization, optimization algorithms. In conclusion, while the brain analogy might be useful once, it is no longer the best way to describe deep learning. Instead, we should focus on understanding the mathematical foundations of the neural networks and their applications in the computer vision and other fields. So that's all for this video, and see you guys in the next one. Until then, keep learning and keep exploring.